Okay, welcome back to the next 5-minute revision series, and we're going to look at processor scheduling. Okay, so first things first, we need to know the idea of what's called a context switch. So that's the idea where you switch from one process to another. This is what the CPU does lots and lots of times whilst you're running it. So each process and the data that the process is using is considered to be a context, and when you switch between them, it allows us to multitask, which allows as a user, we think the computer is running things simultaneously when actually it's not. So the first thing we need to do a context switch for is an interrupt. So what this is it could be anything. It could be a crash, could be a Stack Overflow error, could be where your software breaks. It might just be you plug something in and something needs to appear in the corner. There's loads of different reasons. It's good to think about different reasons why the current thing you're doing might need to be interrupted. So an interrupt is sent back to the CPU by either software, hardware, or by the CPU itself to stop what you're currently doing. So it might be an input-output device, sends an interrupt signal, your printer runs out of paper, there's an error, there's a scheduled interrupt, or something breaks, power failure, and it has to stop what it's doing. So what happens is the CPU checks at the end of each fetch, decode, execute clock cycle, and it checks if there's any interrupts that needs to be processed. If there is, then it does what's called an interrupt service routine. If not, it carries on. So it uses a thing called a stack, which we'll look at a lot later in specification. There's plenty of videos on stacks, but that is a data structure where the first thing is the last out. So any other interrupts get put on top of that, like a stack. If you think of a stack or layers of a cake or stacks of plates, that's the kind of thing. So when an interrupt is detected, the process stops doing any fetch, decode, executes and pushes all the register's data and all the instructions onto a stack. It then uses this thing called the interrupt service routine to process that interrupt, and when it's finished we can pop all the old stuff from the stack and reload it back into the CPU. Now sometimes interrupts have different priorities and these will be processed in that order. So an interrupt could be interrupted if the new interrupt is of a higher priority, and so on. If a higher priority interrupt occurs whilst we're doing that interrupt service routine, then the original interrupt will get pushed onto the stack. We'll complete the higher priority interrupt, do the lower priority one, and then go back to process A. As we said, it's a last in, first out data structure, so the last piece of data that's pushed into the stack will be the first thing that gets done after that. We can also do a thing called process scheduling. So this is where we choose which processes get to be done at any time. It makes it look like it's multitasking. It looks like you've got multiple cores running, but you might just have a single core CPU. So the sort of main goal is to make sure that you don't have anything hanging or waiting, to maximize the time the CPU is used, and if you've got lots of things running or a multi-user system, it's nice and fair for every single process that is waiting. So the first one is a round robin, where each job is allocated a time slice, and it goes through and says, right, process A gets a bit, then B, then C, then A, then B, then C, and it's all nice and equal. Now obviously that could be good, that also could be pretty bad if you've got something that needs quite a lot of processing time and it's got to switch to something else. You've then got first come, first served, so the first job that comes gets executed until it's done. So if you think there's a previous exam question on antivirus, well, if the virus starts running before your antivirus can run because you're on first come, first served, then your computer might be damaged before the antivirus even does a scan. Then you've got shortest time remaining, so the operating system has a little look, figures out which job has the shortest remaining time to complete and does that first. But that does mean that really long processes can get pushed to the bottom of the list indefinitely. Then you've got shortest process next, which we look at the total execution time of each job and then do all the small ones first. But again, you have to worry about longer or bigger applications not running at all. And that's it, roughly on 4 minutes 27 seconds, so that's pretty good. Obviously look for the video again because I do this quite fast. Like and subscribe, and I'll see you in the next video.